Hello. In this presentation, I'm going to talk about linear regression in a more general way, and I will also talk about classification when you have multiple labels or multiple classes, sorry. So this presentation will be divided in 4 parts. A general view of linear regression. Then I will talk about regularization in the case of linear regression. After that, I will discuss discriminant functions for classification and what is the best way to implement this when you have multiple classes. And finally, I will describe one special linear discriminant method, which is called Fisher's linear discriminant. Okay, so we have seen that in linear regression we have a set of points, these blue points, and we want to estimate the parameters of a function in such a way that this function will pass very close to the points that we are given. Given this set of points, in this case we have 10 blue points here. These points were generated using the sine function, and we added some error to these points, so we avoid the points to be exactly over the green sine function. So given these points, we estimated the parameters of a polynomial. In this case, the final polynomial of degree 3 is this red curve. In this case, this capital M refers to the number or the degree of the polynomial. Okay, so this is a degree 3. X is the input variable in this case, and t is the output variable. Sometimes we call this also y variable. In this case, it's a t variable. And w is the parameter vector of our model. Sometimes instead of w we use the letter theta. Okay, so and the data points were generated, as we said, from the function sine 2 times pi x plus some error, just to make it a little bit more complicated, let's say. For our model, that in this case we are calling our model function y, which is a function of the input variable and the parameters of our model. In this case, we are working with a polynomial of degree m, and we need to search what is the best option for the degree of the polynomial. And we also need to learn what are the best parameters, w, for the model, for the degree of the polynomial that we choose. Such parameter vector w can be learned iteratively, for example with the stochastic gradient descent, or we can try to estimate them or learn them directly using the normal equations. So these are the two methods that we can use: an algorithm to estimate the parameters iteratively, or the normal equations. And as we explained before, to be able to apply this, we need this matrix that would result from the multiplication of x transpose times x. We need this result to be matrix that is not singular. So it could be the inverse of this could be computed. And also it is important that our matrix here is not very large. So that all are the conditions that we need to be able to apply these normal equations. There is another way to implement linear regression, and this is called locally weighted linear regression. The idea behind this is to train with more accuracy our model based on the value that we want to evaluate. So for example, if we want to evaluate a point that is over here, it makes more sense to consider more important the points that are closer in the neighborhood of the red point. So our model will take into consideration more these points than the points that are far away. But if we were training our model to evaluate this green point, then we would consider more the close points to the green point. One way to do that is to consider some kind of distance metric or similarity metric, and this is implemented using, in this case, this sigma. This sigma is a measurement of how important each of these points are for evaluating, in this case, the red point or the green point. So one way to implement this similarity metric is using an exponential function in this way. And in this formula, x is the point that you want to evaluate. So if you want to evaluate the red point, here you will put the value of the red point, the x of the red point, and this is the value of each of the points in your data set. And tau is a constant, like the case of the alpha constant, and this number you should define it experimentally. So this is locally weighted linear regression. The only problem with this method is that you always need to keep the points in your data set, because every time you need to evaluate a point, you need to compute the distance or this sigma value for this point with respect to each other point in your data set. And this is something that you don't need to do in the standard linear regression. So with this method you can get more precise predictions, but the problem is that you need to compute these distances every time you evaluate a new point. Okay, we also saw that the polynomial, as we increase the number of terms, we give the polynomial more flexibility, or we create a more complex model, and more complex models can learn more difficult patterns. So at some point that it is good to be able to implement more complex models. For polynomial functions, we need to try systematically different degrees of the polynomials, and this is exactly the same with every other model. We don't know from the beginning, just by looking at the data, what is the best model that is going to solve our machine learning problem. So we need to try, in this case, the polynomials, we need to try with different degrees of polynomials. But if we were talking about a neural network, for example, we will need to try with different topologies of the neural network, different number of layers, different numbers of activation functions, different number of neurons in each of the layers, etc. So we always need to experiment with different models. So what happened with a polynomial function when we try to feed it to some data set if we increase the degree of the polynomial? So in this example here, we see that the model is a polynomial of degree 0. So that means that this is only a straight line that is parallel to the x-axis. If we increase the degree of the polynomial, then we can have some slope here, but it is still very simple, a very simple model for the data that we want to fit. An optimal degree would be 3. In this case, we approximate very well the points. But what happens if we increase the degree to 9? In this case, for only 10 points, these 10 blue points, our model can be trained in such a way that the curve have these crazy curves and manages to pass exactly over each of the points. And this is not good. The error of this model is 0. That could seem to be a good thing at first instance, but remember that the idea of looking for the best model is to be able to generalize. This is to apply this function to evaluate new points. And if you compare the model with degree 3 versus the model with degree 9, this model with degree 3 is going to generalize better than this one, because this one, for example, if you evaluate a point over here, the real value should be something like here in the green curve, but the model is going to tell you something above here. Okay, so these crazy curves are not good, and this is a very extreme case of what we call overfitting. So basically your model has memorized each of the points, and this is not good. We will talk more about overfitting later. Okay, so for each choice of the degree of the polynomial, we can evaluate the performance of the model using the root mean square error. This is a standard way to measure the error of a model in regression, where this e function is simply 1/2 of the sum of the square of these differences for every point in your dataset. This error can also be used to evaluate if our model's performance is improving after each iteration of the learning algorithm, and this is actually what you need to do. After every iteration of your algorithm, you need to plot this error, so you can see that it is really going down and that it is not oscillating, because if it is oscillating, it might indicate that maybe your algorithm is not correctly implemented, or maybe that your alpha is very big and you need to make experiments with smaller alphas, for example. So it is very important to plot the error. Now, what is the best way to plot the error? The best way is to have at least 2 sets of data sets. So for example, that you have available 100 points, then you can take 90 points for the training, and you leave out of the training the remaining 10 examples. So you will have a training set and a test set. So the idea is that you will modify the parameters of your model using only the training examples, and then you will test with the test examples, the remaining 10 examples, for example. And the idea is that you should plot both error curves with the training test, with the training set, and with the test set. And in this particular example of the polynomial, that is trying to fit points generated with the sine function, you would get something like this. In this case, what they are comparing is not the number of iterations, but they are comparing the degree of the polynomial. So they can choose what is the best degree. And what you can see in this plot is that the error in both the training and the test set is going down, and it gets very low with degree 3. If you keep increasing the degree of the polynomial with degree 4, 5, 6, 7, 8, the error is more or less the same. But when you increase the degree to 9, you see that the error of the training set is 0, but the error with the test set just grows exponentially. So this is telling you that you have already overfitted your model, and this is not good, because then the generalization error is going to be huge. So looking at this plot, what you need to see is that starting with degree 3, you already have the best error that you can get, the smallest error that you can get that is actually useful for the model, for predicting. But we will always choose a model with less parameters. So even though a degree 3 and a degree 8 have the same error, we will prefer a model of degree 3, because this means that we will need to train or learn only 4 parameters instead of 9 parameters with degree 8. So we prefer simple models because we can train them faster. Okay, so what about the generalized linear regression? The goal of regression is to predict the value of one or more continuous target variables t given a d-dimensional vector x of input variables. Okay. The simplest linear model for regression is one that involves a linear combination of the input variables in this way. Okay, w0 plus w1 times x1, which is would be the first component of the vector, the input vector, plus w2 times x2, which will be the second component of the vector, and so on. So we can store this x as a vector x, and the key property of the model is that it is linear, is a linear function of the parameters w, from w0 to wd. It is also, in this particular case, a linear function of the input variables xi, because here we are not taking this to some power, it is just the input variable. So this is a very, very simple model. With this model you can create only straight lines, planes, or hyperplanes in higher dimension spaces, and this is very limited. Okay, so we need to make some add some non-linearity to our model, so our models, our lines could be curved and not only straight lines or straight or simply planes. So the way to do that is to introduce this non-linearity, but in the input variables, not in the parameters. So we can keep it simple, we can keep a linear model in terms of the parameters, but we can have non-linearities in the input variable. So the general way to express this is using some function that in this case we are calling this phi or phi function. It is going to be a function of the input vector of variables, and this is called a basis function. So there could be different basis functions that we can apply in order to introduce these non-linearities. So such models are linear functions of the parameters because the parameters are not affected, and this is good because it gives simple analytical properties, especially when we need to compute some derivatives of this. It's very simple because it is linear. and yet can be non-linear with respect of the input variables, and this is good because we can create more complex models with this. It is often convenient to define an additional dummy basis function phi0 of x, so in that way we can rewrite everything as a dot product of w and phi, vector phi. Okay, adding this dummy, and this dummy basis function will output always a 1. Okay. In the case of polynomial regression, it is a particular example of basis function. In that case, our phi function will be defined as xj. So the index over the term of the basis function will work here as a power, so this will be x to the power of j, and this is how we define our polynomial function. Now, one limitation of polynomial basis function is that they are global functions of the input variable. What does this mean? When you say that this is a global function of the input variable, suppose that this x is just a scalar, it's not a vector. It means that every time you take an example, a data point, and you make changes in the parameters, the function, the shape of the polynomial is going to change globally every time you change the parameters of the polynomial for a given example. This is because it's a global function of the input variables, so that changes in one region of input space affect all other regions. So let me go back to a plot of the polynomial, so maybe I can explain this a bit better. So suppose that we are working with this polynomial of degree 3. What they are telling you is that, for example, if you take one example over here and you modify the parameters of the polynomial considering this point here, the whole shape of the polynomial can change. For example, if your point is over here, this update will force your curve to go down, and all the curve is affected. So it is globally affected. It doesn't matter if you update a point that is here or it is here. The whole shape of the curve is going to change. Now there is another option to avoid this, because this could be bad. For example, if you keep training points that are over here, the curve is going to adapt to all these points over here, and maybe it starts to forget, let's say, points that are over here. So this is not good. So we would like to have a function that could be adjusted locally, and one way to do that is using another kind of basis function, not the polynomial. Two good options to do that we will see is the Gaussian or the sigmoid function. So this problem can be solved dividing the input space into regions and fit different polynomial in each region. So this could be one option to use different polynomials, and this is what we call spline functions. Okay. Other options that you can use are Gaussian basis functions and sigmoidal basis functions. So in the case of the Gaussian basis functions, it takes this form. So this is the e number, the exponential of the x, that is the point that you are going to use to update your parameters, and this mu is the center or the mean of the exponential. This exponential, remember that it has a bell-shaped form, so this mu is going to be in the center of this exponential, and this s is simply a parameter or a constant that will allow you to change the width of this bell-shaped function. So it says here the mu govern the locations of the basis functions in input space, and the parameter s governs their spatial scale. So another option would be a sigmoidal basis function, and this has this shape. This is the sigmoidal that we have seen before, 1 over 1 plus the exponential of minus a. And again, you would need to define many centers for this sigmoidal. This would look something like this. In the case of the polynomials, you can define many polynomials, and basically curves that go up or down. In the case of the Gaussians, you will have several bell-shaped functions. You need to define many of these to cover the whole range of your input variable. So here we are assuming that x can take values from -1 to 1, and also the same here, but this is when you are using the sigmoidal functions. Okay. So linear models have significant limitations as practical techniques for machine learning, particularly for problems involving input spaces of high dimensionality. So remember, these are basic models. We can get some degree of complexity or non-linearity using these basis functions, but they are still basic methods. Okay. However, they form the foundations of more sophisticated models such as neural networks and support vector machines. So these are the foundations or more complex methods. Each of these linear models can be seen later as single neurons. So when we build neural networks, we are building arrays of many of these single linear regression models. So if you understand how to apply this the best way, in an optimal way, then you will be able to exploit all the power of neural networks.